video, we now want to take butane, CH3, CH2, CH2, CH3, and we're going to draw that in its staggered conformer. And then we're going to redraw that as a Newman projection. So we're looking down the C2-C3 bond between the two central carbons. You'll notice that when I write the methyl group on the left-hand side here, I'm writing it as H3C, and over here on the right, I'm writing it as CH3. That's to emphasize the fact that the carbon is bonded to the carbon, right? The carbon is bonded to the carbon, not to the hydrogens. And you'll see that kind of conventionally when you're drawing these slightly outlined structures versus showing it as CH3, CH2, CH2, CH3 when I'm writing the condensed form. So I'm going to look down the C2-C3 bond, and I'm going to choose to make C2 the back carbon so that I have the methyl group sticking up on the back carbon, and I'm going to have the methyl group sticking down on the front carbon, because I've been consistent with the other alkanes in having a group sticking vertically up off the back carbon, vertically down off the front carbon. So there's a conformation. It's a staggered conformation, but this is also referred to as an anti-conformation, because the two methyl groups are 180 degrees apart. The dihedral angle between the plane defined by carbon 2, carbon 3, and carbon 4 is 180 degrees off from the dihedral angle defined. B/T is the abbreviation for between, right? So that's a 180 degree dihedral. It's got a special name. It's called an anti-conformation. Now I'm going to rotate this thing, again, leaving the methyl group alone. I'm going to rotate the front carbons of this methyl group. It's going to come over here. You'll notice we now have two methyl over hydrogen eclipsings and one hydrogen over hydrogen eclipsings. If we estimate a 1 kilocalorie per mole strain energy for eclipsing the two hydrogens, which is what we determined from the ethane molecule, and a 1.3 kilocalorie per mole energy difference for each over the hydrogen over methyl eclipsings, we would predict that there should be a total strain energy for this molecule of 3.6 kilocalories per mole. The sum of the two 1.3 and the 1.0 kilocalories per mole. And that turns out to be exactly where that eclipse conformer shows up on the energy diagram of butane, which you can see in your textbook. So now we're going to rotate that 60 degrees, right, to go from the 60 to the 120 degree conformer. That'll be another staggered conformer, the CH3 group now coming up here. So it has no eclipsing strain, but it does have strain. The two methyl groups in this conformation, that's the anti-conformer. And this, where we now have a 60-degree dihedral angle between the two planes represented by carbon 1, 2, and 3, and carbon 2, 3, and 4. That's a 60-degree dihedral angle here. And that's got a special name from the French clumsy called the gauche conformer. So unlike the situation for ethane and propane, our staggered conformers are no longer equivalent. We now have two different energies, the AntiConformer and the gauche conformer. And this strain, the gauche butane strain, from putting the two CH3s 60 degrees apart instead of 180 degrees apart, that strain costs you 0.9 kilocalories per mole. It's a torsional strain. It's caused by two electron clouds passing near each other. But now with a 60-degree dihedral angle rather than a 0-degree dihedral angle, which is what we have here with our H over H eclipsing and our CH3 over H eclipsing. Those are all associated with 0-degree dihedral angles. The 180-degree dihedral angle is strain-free. We can rotate this again. And hit it wrong again. And we can get to our 180-degree conformer. You'll notice that now we have the two methyl groups eclipsed with each other. There's significantly more strain associated with the two methyl groups eclipsed with each other than there would be for a methyl group eclipsed with a hydrogen or a hydrogen eclipsed with a hydrogen. You'll see that those are actually passing quite close to each other. In fact, not only are they passing close to each other, their electron clouds are trying to pass through each other. And that is a different form of strain that we call a steric strain. And that's a significantly larger amount of strain than you would get from a mere torsional strain. So we still have approximately 1.0 kilocalories per mole here for the hydrogen over hydrogen eclipsing, and we have approximately 1.0 kilocalories per mole here for the other hydrogen eclipsing. But the total strain energy for this molecule is actually 4.9 kilocalories per mole. So if we let X in this case equal the steric cost of putting two methyl groups, we know that 1.0 kilocalories per mole times 2, because there are 2 of them, plus X is equal to that total cost of 4.9 kilocalories per mole. And thus X will be equal to 2.9 kilocalories per mole. That's much bigger than the 1.3 kilocalories per mole strain energy for putting a methyl over hydrogen eclipsing and a 1.0 kilocalories per mole that it costs to put a hydrogen over hydrogen eclipsing, reflecting the fact that there's a lot more repulsion caused by two electron clouds actually trying to occupy the same space, passing through each other, than there is between two electron clouds merely passing near each other. So the steric strain, when they try to pass through each other and occupy the same space, is quite a bit bigger, right? It's more than double. 2.6 kilocalories per mole would be double that torsional strain. It's more than double the amount of strain that you would get from the torsional strain. Methyl over methyl eclipsing costs you 2.9 kilocalories per mole. And we have this as our 180-degree conformer. If we go to a 240-degree conformer, I think you can see that this methyl group would move over there. So we would have another different conformer. That would be the 240-degree conformer, and it would be the mirror image of the 120-degree conformer. And then if we rotated another to go to the 300-degree conformer, 60-degree conformer. So 0, 60, 120, 180 is our highest energy where we have that steric strain, 240, 300, 360. So we now know how much strain energy is associated with putting two hydrogens eclipsed with each other, how much strain energy is associated with putting a hydrogen and a methyl eclipsed with steric strain, putting two methyl groups eclipsed with each other, and how much torsional strain we get from the result of putting two CH3 groups gauche to each other. We can put all of that on an energy diagram to scale and see what the energy diagram looks for butane and how that differs from what the energy diagram looks like for ethane and propane. I should point out that when you're asked to draw all the possible maxima and minima, the intermediates and transition states for a given alkane rotating around a particular bond, it doesn't matter which one you start with. I've started in all cases with the most stable conformer, but it doesn't really matter. You can start with any conformer. You'll just have a diagram that's offset by a certain number of degrees. So for butane, the theoretical zero strain, the anti-conformer, is at 0 degrees. And then we have eclipse conformers at 120. Eclipse conformers at 60. Staggered conformer at 120, another eclipse conformer. Right? This is the one that has the methyl-methyl eclipsing. And then 240, we have another gauche conformer. 300, we have another eclipse. 360, we're back to the staggered conformer. So we would start at 0, and we know that the 60-degree conformer had a hydrogen over hydrogen and two hydrogen over methyl eclipsings. So the 60-degree conformer was 3.6 kilocalories per mole above the low point. We know that the gauche conformer was 0.9 kilocalories per mole above. So the gauche conformers are not back down to the theoretical strain free. And then the 180-degree conformer was way up here at 4.9 kilocalories per mole. 300-degree conformer was the mirror image of the 60-degree conformer, and therefore should be at the same energy of 3.6 kilograms per mole, and then back to our 0 point. So we actually have 4 different energies in the energy diagram for butane, whereas we only had 2 different energies for ethane and propane, reflecting the fact that the 2 CH3 groups can be 60 degrees apart. 60-degree dihedral angle is the gauche conformer versus 180 degrees apart. And noting that in one of the eclipse conformers, we have CH3 over CH3, right? Whereas in the others, we only have CH3 over H. The activation energy then for converting one gauche conformer to the other is 4 kilocalories per mole. And the activation energy for converting a gauche conformer back to the anti-conformer is the difference between 3.6 and 0.9, or 2.7 kilocalories per mole. If you start with the most stable staggered conformer, always when you're drawing your energy diagrams, you'll notice that it ends up looking like the thing is giving you the finger, flipping you off, right? Because you'll have your highest energy conformer at the 180, which is in the center of your diagram. But you could start anywhere. I mean, if you started here, that would have been just fine. You would have simply been offset and had the eclipse conformer, the 60-degree eclipse conformer as your higher energy. So your energy diagram would have ended here instead of ending there. But it makes no difference. So we can now use these numbers that we've just calculated for hydrogen over eclipsing of 1.0 kilocalories per mole, methyl hydrogen eclipsing of 1.3, methyl-methyl eclipsing of 2.9, and methyl-methyl gauche 60-degree dihedral angle of 0.9, to calculate the energies of different conformers of other alkanes. And that's what I will ask you to do on the quiz. And there's also an example of doing that in the textbook. Something else that we might like to know, given that our two staggered conformations are now not at the same energy, we can assume that at equilibrium, the molecule is mostly going to be in the staggered conformers, since the eclipse conformers are transition states, right? But these two are different. What would be the equilibrium distribution of the two different conformations, the anti and the gauche conformation? I think we can assume that the anti-conformation is more stable, so it's probably going to be larger than a larger percentage than the gauche conformation. But could we actually calculate the numerical values for what percent is in the anti-conformation and what percentage is in the gauche conformation? Obviously, if the answer wasn't yes, I wouldn't bring it up. You can certainly do that calculation. So I'm going to start by drawing the staggered conformations, and only the staggered conformations, because those are the ones we care about. So here's my most stable conformer, my anti-conformer. And then if I rotate 120 degrees, I'll go to a gauche conformer. It has the CH3 in the front carbon over on the left. And if I rotate another 120 degrees, I'll go to the gauche conformer that has the CH3 on the front carbon over on the right. So I've only drawn the 0-degree conformer, the gauche conformer at 120 degrees, the gauche conformer at 240 degrees. And what I'm going to assume is that at equilibrium, it's only one of these three conformations and not significantly in any of the conformations that are represented by the eclipse conformer. And I'm going to ignore all the intermediate conformations at 5 degrees and 10 degrees and 15 degrees. So what I'm going to say is that at equilibrium, the concentration, or the percentage of 0 degrees, plus the concentration of 120 degrees, plus the concentration of 240 degrees, is equal to 100%, or 1. I know that the energy change from going from the anti to the gauche conformer is plus 0.9 kilocalories per mole. And I know that the energy difference between the gauche conformer 120 and the gauche conformer 240 is 0 kilocalories per mole. And I know, or I should know, from general chemistry, an equation that relates the equilibrium constant to the free energy change for the reaction. So if I know the free energy change for the reaction, I can use that to calculate the equilibrium constant and thus a ratio of the 120-degree conformer to the 0-degree conformer. So I'm going to write the equilibrium constant for this left-hand reaction as KEQ is equal to the concentration of the 120-degree conformer divided by the concentration of the 0-degree conformer. But I'm also going to use that thermodynamic equation that I know tells me that delta G is equal to minus RT times the natural log of the equilibrium constant. And that's a special case of the more general equation that says that delta G is equal to delta G 0 plus RT ln Q. At equilibrium, there is no free energy change. Right, the reaction is spontaneous in neither direction at equilibrium, so delta G is equal to 0, and Q is equal to K at equilibrium, and that's just rearranging that equation and solving for delta G0. Delta G0 is minus RT ln KQ. By dividing both sides by minus RT, I can say that minus delta G0 over RT is equal to the natural log of the equilibrium constant. And then by taking each side to the exponential, e to the minus delta G0 over RT is e to the ln Q. Those are inverse operations. I can say that the equilibrium constant is equal to e to the minus delta G0 over RT. I have a little bit of a complication now, though, because these are delta H's of reaction, and that's a delta G of reaction, a free energy change for the reaction. And the free energy change and the enthalpy change are not, in fact, the same thing. They are related by another equation that you ought to remember from general chemistry that tells you that the free energy change is equal to the enthalpy change minus the temperature times the changing entropy. Delta G0 is equal to delta H0 minus T delta S0. So you would never forget it along with this one. And hopefully, the third equation that you should remember from general chemistry, that delta G0 is also equal to minus N times Faraday's constant times the cell potential E0. Delta G0 equals minus NF E0. That's for electrochemistry. We won't be working with it in this course, so you don't really need to. So now what I'm going to do is I'm going to say there's probably not a lot of entropy change in simply rotating around a carbon-carbon sigma bond. Entropy changes are usually associated with having more molecules on the product side than you have on the reactant side, or having a gas when you used to have a liquid, right? So you have a lot more degrees of freedom. Probably a very small entropy change. So delta S is likely to be negligible for just this simple reaction of rotating around the block. If I make that assumption, the T delta S term will drop out, and I can say that delta G is approximately equal to delta H. And that will allow me to use this delta H value to calculate the equilibrium constant for this reaction. So I can now say that the equilibrium constant is also equal to negative delta H0 e to the minus delta H0 over RT. And I have numerical values for that. So I can say that the equilibrium constant is equal to E to the minus 0.9 kilocalories per mole over R, 8.314 joules per mole Kelvin, times 298 Kelvin. We're doing this at room temperature. And now I just have to convert from kilocalories to calories, 1,000 calories per kilocalorie, and from calories to joules, so that my units will cancel properly. So I can't have units where I take an exponential. So I'll have to multiply that by 4.184 joules per calorie. So kilocalories will cancel, per mole will cancel, Kelvin will cancel, joules will cancel, calories will cancel. And if I plug that into a calculator, I can come up with a value for the equilibrium constant, which I can plug in for the ratio of the 120 degree conformer to the 0 degree conformer. Much simpler for the 120 degree conformer in equilibrium with the 240 degree conformer. Because I know that for this, delta H0 is equal to 0, and e to the 0 power is equal to 1, which means that the equilibrium constant here for the 240 degree conformer over the 120 degree conformer is equal to e to the 0 over RT, negative 0 over RT, but that doesn't really matter, is equal to 1. So that tells me that the concentration of the 120 degree conformer is equal to the concentration of the 240 degree conformer, which actually simplifies my equation a little bit, because remember, the concentration of the 0 degree conformer plus the concentration of the 120 degree conformer plus the concentration of the 240 degree conformer is equal to 1.0, and if these two are equal, then the concentration of the 0 degree conformer plus 2 times the concentration of the 120 degree conformer is equal to 1.0. And I know that I'm going to be able to get my relationship between 0 degree and 120 degree conformation from here. Concentration of the 120 degree conformer is in fact equal to KQ. Q is equal to this number that I just calculated. Since I don't have a calculator handy right now, I'm not going to do that calculation, but I'll leave that as an exercise that you